Hi, today we're going to be talking about section 3.2, solving systems of inequalities by graphing. So we're going to look at intersecting regions, separate regions, how to write and use a system of inequalities, and finding vertices for the system of inequalities. So solve the system of inequalities. So now we're talking about, we're not going to have, remember when we did inequalities before, we get that region, you have that shaded area. Well, now we're going to find out where the two shaded areas cross. So a solution of system of inequalities, like a system of equations, where you find where the two lines meet. Now we're finding where the two regions meet. So that's our whole goal here. So this first example is nice. They're both in y equals mx plus b form, which is a really nice way to be able to put them on a graph. So let's take a look. If I take the first graph, I get a y-intercept of 5, so I'm going to start up here at 5. And then it has a slope of -2, so that means rise over run, so rise -2, or go down 1, 2, run 1. So there's my next point, down 1, 2, run 1, down 1, 2, run 1, down 1, 2, run 1. Okay. It does say equals, so this is going to be a solid line. So I'm just going to draw that solid line. Okay. Now I need to figure out which way do I shade this. So again, plugging in 0, 0 is the easiest way. So if I plug in 0, it goes to 0 is less than or equal to 5. Is 0 less than or equal to 5? Why, yes, it certainly is. So I would shade everything towards the point 0, 0, since that worked. Okay, so that's that part's feasible region. Okay, now let's look at the second one. We'll do the second one in blue. Y is greater than -1/4 x minus 6. So it starts at a y-intercept of -6. Okay, it has a slope of -1/4, meaning I rise -1, which means down 1, over 1, 2, 3, 4. Go down 1, over 1, 2, 3, 4. Okay, so this line is going to look like that. Okay, again, test 0, 0 is 0 greater than -6. 0 is greater than -6, so I need to shade above the line towards 0, 0 again. Okay, so that's everything above. Alright, so my to solve this system, it's where both regions intersect. So notice down here, they do not. Below this line, they do not. Up to the right, they do not. The only place they do is inside this region here. So this is my feasible region in here. So I'm going to shade that a different color just so you can see on this graph the black shaded region is my feasible region. Okay, I do see a little mistake that I made. Maybe you noticed it while I was drawing my blue line. It cannot have, I don't know why this isn't letting me. Well, it's not letting me. That needs to be a dotted blue line, so it should really look like a dashed line here. Okay, and then it would be an open circle where they meet over here because it's a dashed line. Okay, so you try this one, give it a shot, hit pause, and see how you do. Okay, hopefully this is what you got. You can see that absolute value V was the red region, the blue region is the second one, the line, and the black region is the feasible region where that tells us the solution for the system of inequalities. That's where both of these are true. Okay, so if we had separate regions, we're not even going to have you do an example here. I'm just going to do one really quick for separate. If we have this, and there should be a negative sign in front of this first 4 here, -4 plus 4x plus 8. So if I started up here at 8, and I went down 1, 2, 3, 4 over 1, then 1, 2, 3, 4 over 1, down 1, 2, 3, 4 over 1, and the same there. That's about that line. Okay, is 0 greater than 8? No, it's not, so I'd have to shade this one this direction away from 0, 0 if I tested that point. Okay, the second one is the same sloped line, but we're starting at 4 now. So this one, if I just quickly try to draw it parallel. Okay, there we go, same slope, those are parallel lines. Test to 0, 0. Is 0 less than 4? Yes, it is, so I'm going to shade this direction. Okay, this one here has the situation where there's no place where both of these intersect. So really we don't have a solution. These are separate regions, they don't intersect at all. Okay, write and use a system of inequalities to solve this example. Okay, Mr. and Mrs. Rodriguez are driving across the country with their 2 children. Brutal. They plan on driving a maximum of 10 hours each day. Okay. Mr. Rodriguez can drive between 2 and 5 hours per day. Write and graph a system of inequalities that represents this information. All right. They plan on driving a maximum of 2 hours per day. So let's go ahead and define some variables. Let's say x, or the number of hours of Mr. Rodriguez. Okay, so y is the hours of Mrs. Rodriguez. Okay, from there we know that between the two of them, x plus y, the number of hours of Mr. Rodriguez plus the number of hours of Mrs. Rodriguez, are less than or equal to 10 hours because it says they have a maximum of 10 hours. Okay, Mr. Rodriguez can drive between 2 and 5 hours per day. Okay, so that one thing that you can write there is x is greater than 2 and x is less than 5. Okay, that's all the information that we were given, so let's go ahead and draw that. Notice I'm using a 1 quadrant graph because we can't drive a negative number of hours. Okay, well, I know that x and y, I know my x-intercept is 10, because that's in standard form, so plug in a 0 for y and you get 10 equals, or x equals 10. Same thing for the y, so I know that first inequality looks like that, and if I plugged in 0, 0, we'd have this shaded region here. Okay, x is less than, I should say x is greater than, sorry about that, let's change the sign, x had to be greater than 2. So we go over to 2 here, x equals lines are straight up and down, so I'm going to draw that, it's dotted because, or dashed because it's not equal to. So it's greater than 2, so I'm going to go to the right, but also at 5, it has to be another line here that's going to be less than. So I need to stay in between those two and stay in this region here, so I know my feasible region fits right inside here. So this feasible region, any hours, any combination of hours works for the Rodriguez family for driving, so they can do any combination that fits inside that region there. Okay, this will be really important in the next lesson, but we need to be able to find the vertices. Vertices are just where the 2 lines or 3 lines or 4 lines, however many lines we have, it's where they all meet. Okay, so when you draw them, you just have to be looking at which 2 lines meet. So we're just going to solve these like it was a system of equations. Okay, so the first line, if we just look at that, if we're looking at these first 2, where do these first 2 meet? We would be looking at y equals negative 3x plus 6. Well, I can use substitution and plug that into the second equation. So I go 2y, oh, not y anymore, we know what y is. Y is equal to negative 3x minus 6 equals x minus 16. Okay, I distribute. I get negative 6x minus 12 equals x minus 16. So I'm going to move this x over. I'm going to move that 12 over. So I get negative 7x is equal to negative 4. So x equals 4 over 7. Okay, plug that back into the y equation. I get y equals negative 3x. Oh, but I know what x is. X is 4. That was a bad 4, sorry. Over 7 minus 6. So y equals negative 12 over 7. I'm going to change 6 to have a denominator of 7. 6 times 7 is 42 over 7. 42 divided by 7 is 6. So y equals negative 54 over 7. So that first vertice where those first two lines meet is at 4 over 7 comma negative 54 over 7. Okay, sorry for the ugly numbers again there. Alright, then we just need to we have to find the vertices for the other two. So if I'm trying to find where does the first line and the third line meet, I'm going to just use substitution again and go, okay, 11 times y is negative 3x minus 6 plus 7x equal to 12. So that's negative 33x minus 66 plus 7x equals 12. So add 66, I get, let's see, negative 33 and 7 makes negative 26, oops, sorry, negative 26x, which equals 78 divided by negative 26 divided by negative 26. X equals negative 3. We're going to have to move this up here a little. Oh shoot, I won't be able to see that. See if that's enough for me to finish this. Okay, plug in to the y equals negative 3 times negative 3 minus 6. Y equals 9 minus 6, which is 3. So I'm at negative 3 comma 3. Okay, and the last one, I would rearrange. I need to find where the 2y equals x minus 16 is equal to this. So I'm going to just move that 16 to the other side to get that 2x equals 2y plus 16. So then I can plug into the second equation, and now I'll move it because I can see it now. Well, no, I can't yet turn it. So 11y plus 7, instead of x, I'm going to put 2y plus 16 equals 12. 11y plus 14y plus, let's see, 7 times 16 is 112 equals 12. Subtract 112, subtract 112. So I get 25y equals 100. So y equals 4. Plug that into the x equation. X equals 2 times 4 plus 16. X equals 2 times 4 is 8 plus 16 is 24. So that point's 24, comma 4. Those are the 3 vertices for that first problem. Okay, go ahead and give the next one a shot and bring in any questions you have in the class.